Okay, let's unpack this. You walk into your laundry room, right? And you throw a pile of dirty clothes into the washing machine, you press a button, and you just walk away.
Yeah, you didn't even think about it.
Right. You expect the water to flow, the dirt to vanish, and the machine to drain. I mean, it is completely mundane. But what if I told you that lurking just like millimeters behind the drywall of your laundry room is this hidden, high stakes infrastructure grid?
Oh, absolutely.
We are talking about a literal war zone of incompatible materials where volatile chemistry, physics, and high heat problem solving are just colliding every single day just to wash your socks.
It's wild because it is entirely invisible to us until something goes wrong.
Sure.
Like we use these appliances constantly, right? We demand pressurized hot water, pressurized cold water, rapid drainage.
All happening at the exact same time.
Exactly. And yet we take for granted the incredibly delicate balance of, metals and plastics and engineering that actually makes modern sanitation possible.
Yeah, we really do.
So to figure out how this hidden grid actually works, we are diving into some incredible source material for today's deep dive. It's a masterclass walkthrough from expert plumber Claude Taylor. And he's essentially taking us behind the drywall to upgrade a 40-year-old laundry room's water and waste system.
Right. And right off the bat, you realize this is not just a matter of like swapping a hose behind the washing machine. I mean, he is opening up a wall in a house built 4 decades ago,
Yeah, it's a big deal.
which makes me wonder, when you tear down a wall like that, are you essentially opening up a plumbing time capsule? Because you've got this sleek, modern technology, these new fixtures, and they somehow have to shake hands with decades-old decay and just entirely different building standards.
That is exactly the dynamic at play.
Yep.
And that handshake between the old and the new, it is incredibly fraught with risk.
Oh, I bet.
I mean, before you can even think about installing a sleek, modern laundry system, you have to dismantle the old setup, and it has to be done surgically.
Wait, surgery?
Yeah. When you're dealing with a 40-year-old plumbing system, you cannot just grab a heavy wrench and start yanking on pipes.
Wait, why not? I mean, if you're replacing the pipes in that wall anyway, why does it matter if you're a little rough taking the old ones out? Aren't they going to the scrapyard regardless?
Well, they are, but the rest of the house isn't.
Oh, right.
Yeah. The source material details this highly specific technique. He uses 2 wrenches to break down the old galvanized steel pipe. You use 1 wrench to hold the main pipe absolutely still, like anchoring it in place.
Okay.
Then you use the second wrench to actually turn and loosen the fitting. You are actively isolating the torque.
Ah, I see.
Because if you only use 1 wrench and just pull hard,
Mhm.
that twisting force travels down the pipe, into the wall, under the floorboards, and it puts immense stress on every other aging joint in the house. You could easily snap a brittle, threaded joint in a bathroom 3 rooms away.
Oh, wow. So you might successfully fix the laundry room but cause a catastrophic hidden leak somewhere else entirely. So you're basically trying to contain the trauma of the renovation to just that one exposed square foot of wall.
Precisely. You want to keep the trauma localized. And speaking of trauma, one of the most revealing moments in the walkthrough is when he finally gets that old galvanized steel pipe off and looks inside.
Oh, yeah. That part was gross.
It really is. You might look at the water pressure from your sink and think, hey, my 40-year-old pipes are doing great. But he points out that these old pipes eventually need replacing, not just because they might rust through from the outside.
Right, which is what you'd expect.
Yeah, but because of an invisible, silent chokehold happening on the inside. It's severe calcium buildup.
But how does that even happen? I mean, water is flowing through it constantly. Shouldn't that, like, wash the inside of the pipe clean?
You would think so,
Yeah.
but it is actually the water itself causing the issue.
Wait, really?
Yeah. Over decades, dissolved minerals in the water, specifically calcium and magnesium, they begin to precipitate out, and they deposit themselves on the rough interior walls of the galvanized steel.
Oh, so it just sticks to it.
Right. We call it scale. And layer by microscopic layer, the internal diameter of that pipe gets narrower and narrower.
Like an artery slowly clogging?
That is a perfect analogy.
Yeah.
The water pressure, like the force of the water pushing against your thumb, if you hold it over a faucet, that might feel perfectly fine to you.
Yeah, it feels strong.
But the actual volume of water able to pass through that pipe is drastically reduced, Eventually, it just becomes a complete bottleneck.
So you've got these choked up old steel pipes, right? And you need to connect them to fresh new copper lines for the modern setup.
Correct.
But the source material is very clear about this. You cannot just screw a new copper pipe directly onto an old galvanized steel pipe.
No, definitely not.
You have to use this highly specific middleman piece. I think it's called a dielectric union, along with something called true blue pipe sealant. And this is where the chemistry really threw me. Why can't metal just touch metal?
Well, because if you let copper and galvanized steel make direct physical contact, and then you introduce water flowing through them, you initiate a process called electrolysis.
Okay, here's where it gets really interesting. Wait, so by just connecting two incredibly common plumbing metals together, you accidentally build a slow-motion battery inside your walls.
That is the exact mechanism.
Yeah, that's insane.
It is. The
Yeah.
water acts as an electrolyte, like a conductive solution. And the two different metals, the copper and the zinc-coated steel, they act like the positive and negative electrodes of a battery.
Right.
Because of their different properties on the galvanic scale, electrons literally begin to flow back and forth between the copper and the steel.
Oh, wow.
And this electrical current causes galvanic corrosion. It eats away at the metals prematurely. And surprisingly, the newly installed copper is often the metal that ends up corroding, pitting, and failing faster than the old steel.
That is wild. I mean, you spend all this money on premium copper piping, and you end up dissolving it from the inside out just because it touched a piece of steel.
Exactly. It's an expensive mistake.
But I have a fundamental point of confusion here. If the dielectric union stops this by putting, like, a plastic insert and a black rubber seal between the two metals,
Yeah.
how does that not just block the water? I mean, if the whole point of a pipe is to let water flow through, how are we isolating the metals without plugging the pipe entirely?
Oh, that is a great question. The dielectric union is not a solid plug. It is a specialized collar.
A collar, okay.
Think of it like a tunnel with a specialized lining. The plastic insert and the rubber ring, they form a gasket that sits exactly at the rim where the two pipes meet.
Ah, I see.
So they form a non-conductive barrier around the circumference of the connection. The water still flows right through the open center, but the copper metal and the steel metal never actually physically touch each other.
Right, right.
And no physical contact means no circuit. No circuit means no electrolysis, and your new plumbing survives.
It really reframes how you look at the hardware store aisle. You know, it's not just a bunch of metal tubes and fittings. It's an active science experiment you're putting into your house.
It really is.
And the walkthrough also mentions needing that true blue pipe sealant on the threads of that union. What is that actually doing? Is it just, like, glue?
No, it is not glue at all. It's a thread sealant, and it works on a microscopic level.
Microscopic?
Yeah, when you look at the threaded end of a metal pipe, it looks perfectly smooth to the naked eye, right?
Yeah, feels smooth too.
But under a microscope, machined metal is full of jagged peaks and valleys. When you screw two metal pipes together, those microscopic imperfections leave tiny gaps where pressurized water can easily snake its way out.
Oh, and water will always find a way out.
Always. So the sealant fills all those microscopic voids. It acts as an impermeable gasket that ensures a watertight seal, while also lubricating the threads so you can actually tighten them down properly.
It is amazing how much invisible physics and chemistry goes into just getting clean water into the washing machine. But bringing water in is really only half the battle.
Right. Getting it out is the other half.
Exactly. Once that washing machine drains, getting the dirty wastewater out introduces a completely different set of physical hurdles. The walkthrough shifts from the volatile chemistry of the incoming water lines to the frustrating material science of the outgoing drain pipes.
Oh yeah, the drainage is a whole different beast.
And it proves that plastic is just as temperamental as metal.
Indeed. We shift entirely to the physics of drainage. In this scenario, he is dealing with two completely different types of plastic.
Right.
The existing pipe in the wall is a white pipe, which is PVC, and the old pipe he needs to cut out is a black pipe, which is ABS.
Okay, let's pause there for a second because those acronyms get thrown around a lot. I know PVC is the classic white pipe you see everywhere, but what do those actually stand for and why does the difference matter so much?
Sure. So PVC stands for polyvinyl chloride.
Mm.
It is rigid, highly durable, and very common in modern plumbing.
Okay.
ABS stands for acrylonitrile butadiene styrene. It's an older standard, often black. And the key difference lies in that last word, styrene.
Styrene. Okay, what does that do?
The styrene in ABS makes it slightly softer, more shock-resistant, but crucially, it gives it a significantly lower melting point than PVC.
Ah, and that lower melting point leads to one of the most hilariously frustrating moments in the whole walkthrough.
It really does.
Claude needs to cut through this black ABS pipe in a really tight spot inside the wall, so he tries to use this specialized cutting cord. It's basically a flexible wire covered in abrasives that you saw back and forth to slice the pipe.
Right.
He says the cord cut through the plastic incredibly fast, but there was a massive catch.
Yes, a textbook lesson in the laws of thermodynamics right there.
Right. The friction from pulling that cord back and forth generated so much heat that the ABS plastic didn't just cut, it melted into a literal liquid right at the cut line.
Yeah, it liquefied.
And before he could even pull the two halves of the pipe apart, the plastic cooled and instantly fused itself back together.
It completely welded the pipe shut by trying to cut it.
It's like trying to drill through a block of ice with a red-hot drill bit. You melt the hole incredibly fast, but the second you stop spinning the drill, the water refreezes and locks your tool completely solid inside the ice.
That is a perfect analogy. The immense localized heat from the friction liquefied the styrene in the ABS.
Wow.
Now, PVC, having a higher melting point, might have just shaved off into plastic dust under that same friction wire. But the ABS turned it to a viscous liquid and rebonded.
So the tool was entirely wrong for that specific plastic.
Exactly. It illustrates that you cannot treat all plastics as if they are the exact same material. He had to abandon the fancy friction cord entirely and use a small traditional handsaw to slowly cut it without generating all that heat.
I can only imagine how often an enthusiastic DIYer makes this exact melting mistake on a Saturday afternoon. You know, assuming all plastic pipes are basically the same. And suddenly they've accidentally manufactured a solid block of plastic where their drain used to be.
Oh, I'm sure it happens all the time.
But the material quirks don't stop there, because once he finally gets the ABS pipe cut with a handsaw, he has to connect the new white PVC to the old black ABS. And you can't just slap some plumbing glue on them and stick them together.
No, you absolutely cannot. And this raises a really important question about chemical bonding.
Okay.
The standard chemical solvents used to bond PVC pipes together are actually welding agents. They literally melt the surface layer of the plastic to fuse the two pipes into one continuous piece.
Right, it's not just sticky, it actually melts them.
Exactly.
Yeah.
But because ABS and PVC have entirely different chemical makeups, a solvent designed to melt PVC will not properly react with ABS.
Oh, so it just won't hold.
Right. If you try to glue them, the bond will be weak, it will eventually crack under pressure, and you will have raw, soapy washing machine wastewater leaking directly into your wall cavity.
Yikes. So what is the workaround? If you can't glue them, how are you supposed to connect them?
You isolate them mechanically, similar to how we handled the incompatible metals earlier.
Okay, how does that work for plastic?
You use a transition piece called a no-hub band. This is a thick rubber sleeve. In this case, a 2-inch standard size for laundry waste. You wrap this rubber sleeve around the joint where the PVC and ABS meet.
Just wrap it around.
Yeah. And over that rubber, there is a corrugated stainless steel shield with metal worm clamps.
Oh, I've seen those.
Right. You slide the PVC into one end of the rubber, the ABS into the other, and you mechanically crank down those metal clamps.
Okay.
The clamps compress the rubber incredibly tightly against both plastics, creating a permanent, watertight friction seal that completely bypasses the need for chemical glues.
That is so clever. Standardization in construction really relies on these unsung heroes. I mean, transition pieces like the dielectric union for metal and the no-hub band for plastic are essentially the universal translators of the plumbing world.
They really are.
They prevent catastrophic failures when generations of building materials just collide in the same wall.
Exactly. They bridge the gap between decades of changing building codes.
So we've successfully dodged the electrolysis battery, we've navigated the melting plastic drainage, and now it's time to actually build the new water supply system.
Right, the fun part.
Which involves bringing a literal 2,000-degree open flame blowtorch into the confined space of a wooden wall.
Yeah, this is where the physical, spatial demands of the trade really come into focus. He is soldering the new copper joints together using a standard propane gas bottle like the kind you can buy at any local hardware store.
Yeah.
But he is utilizing a very specific tool attached to it, a $40 auto start tip.
Right, so he doesn't need to sit there fumbling with the spark striker to ignite the gas while his hands are shoved inside a dark wall cavity.
Exactly.
You just click the trigger and you have a perfect flame. But even with the convenient torch, he introduces this crucial strategy called pre-fabbing or prefabricating. He doesn't just start welding pipes together inside the wall. He takes his measurements, cuts the copper, pieces it together, and then solders the majority of those joints out in the middle of the open room, completely away from the wall.
Right.
Why go through the extra step of building it outside just to carry it back inside?
Well, if we connect this to the bigger picture of working in the trades, prefabricating isn't just a matter of convenience. It is a fundamental strategy for risk mitigation.
Risk mitigation, okay.
Think about the environment he is working in. He is dealing with 40-year-old framing studs, dry paper backing on the surrounding drywall, and likely old, highly flammable insulation.
Right, basically a giant tinderbox.
Exactly. Bringing an open flame into that environment is inherently dangerous. By prefabbing the complex angles and multiple joints outside the wall, he minimizes the amount of time that flame is active in a hazardous zone.
So prefabbing is basically like a surgeon doing their toughest, most intricate suturing on a brightly lit, sterile table before putting the organ back into the patient. You do the hard work where you have the space and the light to do it perfectly.
That's a great way to look at it.
But wait, how does soldering actually work? Does he just like melt metal over the joint and hope it drips down into the crack?
Oh, no, not at all. It relies on a fascinating physical phenomenon called capillary action.
Capillary action.
Yeah. First, he cleans the copper and applies a chemical paste called flux. The flux cleans off oxidation. Then he heats the copper fitting with a torch. Now, importantly, he heats the pipe, not the solder wire itself.
Oh, so the pipe melts the metal?
Exactly. Once the copper reaches the melting point of the solder, he touches the wire to the joint. Because of capillary action, the liquid metal actually defies gravity.
Wait, it goes up.
Yes. It gets sucked up and drawn deep into the microscopic gap between the two pipes, following the heat and the flux. It fills the void completely, creating a perfectly sealed, incredibly strong joint.
That is amazing. The liquid metal actually pulls itself upward against gravity.
It's really cool to watch.
But I mean, even with prefabbing, he eventually has to make those final soldering connections inside the wall to attach his new assembly to the main water lines.
He does, yeah.
And his safety protocol for doing that is brilliantly simple. He keeps a cheap spray bottle of water right beside him.
So simple, but so effective.
Right. He actively mists down the back of the drywall and the wooden studs before he lights the torch.
Oh.
He keeps the surrounding materials damp so the flame doesn't accidentally ignite a hidden house fire.
It is a constant exercise in spatial awareness and anticipating disaster.
Yeah.
I mean, the highest tech solution he has is an auto-start blowtorch, but his primary safety mechanism is just a dollar store spray bottle of water. Yeah.
I just love the practicality of that. But honestly, my absolute favorite part of this whole prefabbing sequence was this brilliant, low-tech physical hack he uses.
The egg shaping.
Yes. He is trying to measure and dry fit this complicated setup of pipes and elbow joints before he solders them. But if you slide a round copper pipe into a round copper elbow fitting, it's loose.
Right, there's play in it.
Gravity takes over and the pipe just swivels and swings around under its own weight. It's incredibly frustrating because you can't get an accurate measurement if the pipe keeps drooping out of place.
Exactly. Gravity is actively working against your precision.
So what does he do? He takes his pliers and gently squeezes the very end of the round copper pipe. He just pinches it to make it slightly egg-shaped, just barely out of round.
Yep.
Then, when he shoves it into the perfectly round elbow fitting, that slightly wider egg shape creates a tight friction fit. The pipe bites into the inside of the fitting and holds itself completely rigid at the exact angle he needs without needing to be soldered yet.
It's genius.
He can step back, check his measurements, and the pipe isn't swinging around.
It really speaks to the deeply embodied knowledge of the trade. You know, an engineer might sit at a desk and design a complex mechanical clamp to hold the pipe in place during measuring.
Right, some $50 tool.
Exactly. But the person actually in the field, sweating in the laundry room, realizes that slightly deforming the pipe with a pair of pliers achieves the exact same result in 2 seconds.
Yeah.
It is applied physics used to overcome gravity. And all of these steps, the prefabrication, the capillary action soldering, avoiding the plastic melting, all of it is leading up to the installation of the system's brain, the actual modern laundry box.
Yes, the laundry box. We've talked about all this chaotic chemistry and physics happening behind the wall, but the box is the only thing you, the homeowner, actually see once the drywall goes back up.
No.
It's that white plastic recess set into the wall where your washing machine hoses plug in. And Claude points out the brilliant modularity of these modern boxes. It has 3 holes in it. And you can configure it however it is most convenient for the layout of the room. You can have the hot and cold water valves on the two outside holes and the waste drain in the middle.
Or you can shift the drain to the far right.
Yeah, you can even flip the entire box completely upside down if your water lines are coming from the ceiling instead of the floor.
It is a triumph of flexible, user-centric design. The box adapts to the environment rather than forcing the plumber to adapt the environment to the box.
Which is how it should be.
Absolutely.
Yeah.
But amidst all that incredible flexibility, there is one universal, completely inflexible plumbing rule that he emphasizes.
Oh, the hot and cold rule.
Yes. No matter how you orient the box, no matter where the pipes are coming from, the hot water valve is always on the left and the cold water valve is always on the right.
Always. I mean, the box itself is basically the USB-C port of plumbing. It's infinitely reversible and adaptable, but that one rule is sacred.
It is.
But I have to push back a little here. Does that really matter for a washing machine? It's just a machine reading a sensor. It doesn't know left from right as long as the hoses are labeled. Why is that rule so universally protected across the entire industry?
Well, because consistency prevents injury. And plumbing codes are written for human beings, not just machines.
Okay, fair point.
Imagine someone staying at a hotel or a guest in your home, turning on a shower or a bathroom sink. If hot and cold were randomized based on what was easiest for the plumber on that specific day in that specific building, people would get severely scalded constantly.
Oh, wow. Yeah, you just turn the knob out of habit.
Exactly. By making hot on the left, cold on the right, a universal constant across every fixture from a high-end shower to a hidden laundry box,
Yes.
muscle memory takes over. We interact with water systems safely by instinct, completely regardless of what building we're in.
That makes total sense. It is foundational user interface design, just implemented with copper and water instead of software.
Sure.
And speaking of the interface, watching him actually install the box is deeply satisfying. He uses this versatile 6-way screwdriver where you can, like, pull the metal tube out, flip it, and it instantly turns into a nut driver.
Those are great tools.
Yeah. He uses it to strap the box down tightly to the wooden wall studs. It is totally secure. But then he does something that really struck me. This is a renovation, right? He knows for an absolute fact that the drywallers are going to come in the very next day and cover up everything he just did with brand new opaque wallboard.
Yes, he does.
But despite knowing it will be hidden forever, he still takes the time to ensure the setup is perfectly neat, properly aligned, and meticulously trimmed out.
He really takes pride in it.
Right. I was watching this thinking, nobody is ever going to see the beautiful capillary action soldering job. Nobody is going to see how perfectly level and parallel the pipes are behind the wall. Why bother putting in that level of aesthetic effort for something that is going to be instantly buried in the dark?
Well, if we connect this to the bigger picture, it is the philosophy of invisible craftsmanship.
Invisible craftsmanship. I like that.
Yeah. Doing something neatly behind a wall isn't just about personal pride, although that is certainly a huge part of the trades. It actually sets up the next person for success.
Oh, right. The drywallers.
Exactly. When the drywaller arrives the next morning with their tools, if that laundry box is perfectly flush with the studs and rigidly secured, their job of cutting the drywall to fit snugly around it becomes infinitely easier. And it yields a much cleaner final result.
So he's actively making the next guy's day better.
Exactly. Furthermore, a system that is installed neatly with pipes running parallel, properly strapped down, without unnecessary tension or bending, is a system that operates reliably for decades.
Because it's not stressed.
Right. When you turn on a washing machine, water rushes through those pipes with immense force. If the pipes are installed haphazardly, they will rattle against the wood when the water pressure shifts.
Oh, I've heard pipes bang in the wall before.
Water hammer, yeah. And they will stress the solder joints over time, eventually causing a leak. So invisible neatness directly translates to visible longevity.
So what does this all mean for us? We started by looking at a completely mundane chore, throwing socks into the laundry. But peeling back the drywall revealed an incredibly dynamic environment.
It really is a whole different world back there.
We watched a master carefully isolate the twisting torque of 2 wrenches to avoid shattering a house's delicate, aging infrastructure. We learned how to avoid building a slow-motion, pipe-destroying battery through the chemical isolation of a dielectric union. We saw firsthand how the intense heat of a friction shortcut can literally liquefy and fuse plastic, forcing a reliance on mechanical no-hub transition bands.
And we observed the necessary foresight of prefabricating with fire to mitigate risk, utilizing applied physics like capillary action to seal joints and the simple egg-shape hack to fight gravity. And finally, we saw the installation of a smart, modular box anchored by the universal safety rule of hot on the left, cold on the right, all wrapped in the ethos of invisible craftsmanship.
The walls around you right now, in whatever room you're sitting in as you listen to this, are packed with these invisible, perfectly engineered solutions. There are thousands of tiny choices made by tradespeople happening right behind the paint, designed to keep the chaos of chemistry and physics safely contained so you never have to think about it.
Which leaves us with a lingering thought to consider. Think back to that calcium slowly, silently building up inside those 40-year-old galvanized steel pipes.
The clogged artery.
Right, narrowing the flow over decades, layer by microscopic layer, even while the water pressure felt perfectly fine to the homeowner. It makes you wonder, what other invisible systems in your life, your daily habits, or your own home are slowly accumulating buildup right out of sight, just waiting for the day they finally demand a total upgrade?